Sure. It's too lean. There's not enough fat in it. It's hard to cook with. Rational functions. Okay. As of now, we should be experts at polynomials. Know everything there is to know about polynomial. Be able to tackle any polynomial question that comes at us, whether it's a question like we've seen before or not. Right? To the fullest extent. Well, now it's time to learn something a little bit new. Now, for this week, we will only be tackling rational functions as a complete review of the concepts you learned in Algebra 2. So while this stuff will show up on Friday's test, should be a complete review. Should be pretty easy. Today, my hopes are to keep it completely conceptual, probably spend most of the lesson just typing new things into GeoGebra and seeing what it looks like and stuff like that. But first of all, what is the definition of a rational function? What is the definition of a rational number? Any number that can be written as a fraction. So therefore, pi must be rational because I can write it as a fraction. No. It's any number that can be written as a fraction, where the numerator and denominator are what? Integers. That is the definition of a rational number. Any number that can be expressed as a fraction, where the numerator and denominator are integers. Okay? Well, what's a rational function? It's a function that is a fraction, but where the numerator and denominators are what? Polynomials. Okay, so the numerator must be a polynomial, the denominator must also be a polynomial. That's the definition of a rational function. So, one of the things we do when we analyze rational functions is we analyze the numerator, we analyze the denominator. So being able to analyze polynomials is really the key to analyzing rational functions. Right? Okay. So let's create a basic rational function. Let's create a linear 2x minus 3 over another linear x minus 5. Is that a rational function? Is that a polynomial over a polynomial? Absolutely. 2x minus 3 over x minus 5. However, is it itself considered a polynomial? Absolutely not. For example, what is the domain of all polynomials? All reals. But what is the domain of this function? All real numbers except for the number 5, right? Something is clearly happening around this number 5. What is happening around this number 5? Somebody give me a number that's really, really close to 5. 4.9. I heard 4.3. So I'm going to take 4.3. I'm going to store that in for the variable x on my calculator. Okay? And then I'm going to ask my calculator, hey, what is 2x minus 3 divided by x minus 5? And it gives me negative 8. Okay, that's great. Give me a number that's even closer to 5. 4.9. So let's take 4.9, store that in for x. Does anybody know how instead of retyping that 2x minus 3 divided by x minus 5, I can just... Yeah, I think you can use the up arrow, or you can hit second enter a couple times. So then just hit second enter a couple times. So now, my input was even closer to 5, and my output just went to negative 68. Let's try a number that's even closer, like 4.999. Store that in for x.
Is there a calculator you can do the repeat function?
No. Hit second enter twice. Like we said yesterday, your calculator cannot store an infinite number of decimal places. Hit enter again, and it gives me negative 6,998. So if I try 4.999999, and store that in for x, and try that one again, I get, oh my, something even more negative. So what's happening? As x gets closer and closer and closer to 5, what is the output getting closer and closer to? Negative infinity. Now, I was only approaching x from what direction, the left or the right?
The right.
The left. So the way this works is, as x approaches 5 from the left, f of x is approaching negative infinity. So some of the ways you might write that, like f of x is approaching negative infinity as x approaches 5 from the left. You put a little negative sign, because isn't the negative direction of a number always going to be to its left? Right? So that's our way of saying, as x approaches 5 from the left, f of x approaches negative infinity. Sometimes you might see this written using notation like this. The limit, as x approaches 5 from the left, of f of x equals what? Trick question. Can you ever equal negative infinity? So technically we say that this limit doesn't exist, but you can describe that the function is going down to negative infinity. But just a little intro to some notation we'll be using with this idea of limit. Now, what do you suppose is happening to f of x as x approaches 5 from the right side? Right? So, if I take the number 5.000000001, which is really, how far apart is this number from the number I was previously tested? Not very far apart. But watch how far apart their outputs are going to be. There. Whoa! Take that decimal place and move it to the right 12 times. That's a huge number. What is that? What is that number? Yeah. 7 trillion. Holy moly. So it turns out f of x is approaching positive infinity as x approaches 5 from the right. So we've got a graph that's doing this at 5. From the left down to negative infinity, from the right up to positive infinity. What is the reason for that? We have a fraction whose bottom is approaching what? 0. But what is the top approaching? What do you get when you plug 5 in for x up here? You get 7. Now, the reality is, what is 7 divided by 0? Undefined. Try it on your calculator. 7 divided by 0 is undefined. Okay? But, if you have something that is approaching 7 on the top, and the bottom is approaching 0, what do you get when you take something like 6.9999999 divided by 0.000001? You get something huge. It explodes. So I want you to be able to look at something and say, what is the bottom approaching? It's approaching 0, but the top is approaching 7, and automatically know that's infinity, or negative infinity, and so on. Okay? We can see this. Let's graph this in GeoGebra. Yeah. Would you rather have it tonight or the night before a test?
Wait, are we gonna have
Okay, still do it.
Are you gonna collect it?
I'm not planning on getting homework tomorrow night, no.
Are you gonna collect it?
I could. I love collecting right after I collected, so when people expect it the least.
Well, we already expect it.
18 environmental science, but not each year.
Okay.
So,
Take it Monday.
That's
If you have a study hall, I'll take it during study hall.
so much fun.
so we take it Friday.
Oh, you're not going to be here tomorrow? Oh, tomorrow. No, watch the video. You can still take it class Friday. Yeah. You don't have to ultimately, but I think in your best interest, the plan would be watch the video tomorrow's lesson and then take the class Friday. I think if you wait over the weekend and stuff, I think I think you'll get a better grade if you prepare to take it Friday and just take it Friday. Okay. That looks good. All right, let's graph this. Here's what I'm going to do. I'm going to make a slider here. Let's make that slider go from -10 to 10. Let's make it go up by 0.01s. That looks good. And then I'm going to make a point whose x-coordinate is the x-coordinate of that slider. But the y-coordinate is going to be, what was that equation? 2x minus 3? Over x minus 5. So here's what we have. We've got this slider that controls that point, and that point follows the shape. And so I can actually trace this. I can animate this slider. Oh, sweet. Watch what happens as it approaches the number 5. Zoom! Okay, watch as it approaches 5 from the right. It goes up to positive infinity. Okay? So the slider is the x-coordinate of the point. As you approach 5 from the left, the graph goes down to negative infinity. As you approach 5 from the right, it goes up to positive infinity. Pretty neat? Okay, and then we can actually tell GeoGebra, turn the tracing. Let's actually have it graph this equation. Now y equals 2x minus 3 over x minus 5. Okay, there's the actual graph, absolutely. And so that's what you have, right? Remember these graphs from Algebra 2? We already determined that this graph has a what at 5? What type of asymptote? It's a vertical asymptote. Now, what is an asymptote? Okay. Can a graph cross through an asymptote? Yes. Absolutely. Can a graph cross through an asymptote? For sure. It is not this barrier that you are not allowed to ever touch or cross. Okay? For example, here, I'll show you a graph that has an asymptote. X times sine. No, that's not a good example. How about sine x divided by x? Okay, that graph has an asymptote. The x-axis is the asymptote for this graph. See how it has see how the first hill is pretty big? So then the second dip is smaller, and then the next hill is even smaller yet, and even smaller yet. What is this graph slowly approaching? 0. But how many times does it actually cross through the value of 0? Infinitely many times. But the key is, it's getting slowly closer and closer and closer to this horizontal line of 0. Now the thing is, does every graph have some sort of asymptote? Usually when we say asymptote, asymptote implies a line, straight line. And for that reason, not every graph turns linear or looks like it's becoming more and more linear. That is not true. Like, for example, here's a graph that clearly does not have any asymptote of any kind. See how it just continues waving forever and ever. It never starts to look linear. Okay? So no, not every graph has an asymptote. Now, can a function ever cross a vertical asymptote? No. Okay? Could I create a graph that crosses through a vertical asymptote? Absolutely. But is there any way it could still be a function? No way. Imagine this is a vertical asymptote, and I've got this graph that's coming along here, and then it does this. It crossed through the vertical asymptote. But is it a function? No, it can't be. How can you possibly cross through a vertical asymptote but then approach it, but still be a function? You can't. Okay? So you never see it with vertical asymptotes, but do you ever see it with horizontal asymptotes? Yes. You know, I could have a graph that's going like this, and then it goes, and then it goes like that. Cross through that horizontal asymptote a lot. Okay? Do all asymptotes have to either be perfect vertical lines or perfect horizontal lines? No, it could be a line with some sort of slope. We call that an oblique or a slant asymptote. Okay? But here's the idea. Okay? So this graph has a vertical asymptote because the bottom of the fraction approached what? 0 as the top approached what? 7. Whenever you have a number really close to 7 divided by a number really close to 0, you get this explosion, and you see that in the graph as a vertical asymptote. Now, if I were to zoom out on this graph a lot, what percentage of that graph really was the vertical asymptote? Tiny, right? How much of that graph? Now that we've zoomed out a lot and I can't even see it, most of this graph is this very, very boring, almost basically horizontal line. So does it ever get perfectly horizontal or perfectly straight? It's always got a little bit of curvature to it, but not much. 99.999% of this graph just looks like a horizontal line. It really does. We call this the global scale. Whenever you zoom out on a graph so much that all you see is end behavior, you're zoomed out so far you can't even see what's happening in the middle anymore. We call that the global scale of the graph. And in the case of this particular, it's a horizontal line, which, by the way, when you divide a degree 1 polynomial by another degree 1 polynomial, what type of polynomial might you expect? What's 1 minus 1? Degree 0. And what does the graph of a degree 0 function look like? A horizontal line. Okay? So let's create another example so I can emphasize this even more. So as we zoom back in, we start to see more of that middle behavior. As you zoom in really far, does this graph look like a horizontal line at all? No. But the reality is, most of its life is spent looking like a horizontal line. A horizontal line is what that graph really wants to be. But because that vertical asymptote is just that one little flaw in the middle that messes it up. Let me create another graph to really emphasize this. Let's do a degree 2 about x squared plus 6x plus 8 divided by x minus 3. That's a degree 2 divided by a degree what? What would you normally expect when you divide a degree 2 by a degree 1? A degree 1. And what do the graphs of all degree 1s look like? Lines. Specifically, not horizontal or vertical lines. Lines with some sort of slope. So I am predicting the graph of this function is going to be a line. And I'll even go ahead and tell you it's going to be a line with slope 1. But if I type this into GeoGebra and actually look at what this graph looks like, I'm not going to get something that looks like a line of slope 1. What am I going to get? Let's type this in. Let me delete these. We don't need them anymore. Y equals x squared plus 6x plus 8 divided by x minus 3. Wow. Does that look like a line of slope 1 to you? No, not at all. Look at all that curvature. That's not a line of slope 1. Not one bit. Is that a line of slope? Wait a minute. By golly, that looks like a line of slope 1. That's crazy. Right? Most of this graph looks like a line. Now, any idea how I can actually get the equation of the line this guy is trying to be? Let's divide this thing. X squared plus 6x plus 8 divided by x minus 3. Oh, let's do synthetic, yes. I'll accommodate you lazy mathematicians. Yeah, I don't know what she is talking about. So what we end up with is x plus 9 plus the remainder 35 over x minus 3. Now, here's the idea. We're talking global scale. When we zoom out really far, most of our graph is filled up by x-coordinates that are huge. What happens to this fraction when the input is huge? It is basically 0, so let's ignore that. Let's pretend it's not even there. This line, x plus 9, that is the line that we are seeing right here. Okay? Let's zoom back in. Let's graph y equals x plus 9 and see if these match up and these are consistent. Y equals x plus 9. Look at that. It went through there perfect. You see that? The fact that I couldn't really see it graphed is a good thing, right? That means they lined up very, very well. Okay? What do we call this line? What's a special name for it? Oblique or slant asymptote. Now I'm going to do you one even better. Let's take a degree 3 polynomial. No, let's do even better than that. Let's take a degree 6 polynomial for the numerator, and let's do a degree 4 polynomial for the denominator. Because usually, if they divide perfectly, what do you get when you divide a degree 6 by degree 4? Or what does a quadratic look like when you graph it? So I'm telling you, if you graph a rational function where the top is a degree 6 and the bottom is a degree 4, it'll look like a parabola. What if the bottom's a higher degree than the top? Then it's going to look just like the x-axis. It's just going to look like a zero. Yeah, we'll be reviewing that tomorrow in more detail. Today's just, let's just look at some graphs. So I'm going to type in, I'm just going to make up a degree 6. So let's delete this one. Okay, zoom in a little bit here. Get a nice close view. So this is going to be y equals, I need to create a degree 6. So how about x minus 1, x plus 3, x plus 7, x plus 2, x, how many is that? And x minus 6. Great. Now let's create a denominator. How about x minus 3, x plus 1, x minus 2, one more? X plus 6. How about that? Does that work? Okay, graph. Whoa! Does that look like a parabola to you? And I bet you we're not even seeing this whole graph, actually. This is crazy. This is so exciting. You're right. Let's start zooming out so far that we can't see any of that middle behavior, all that junk that's happening. We're kind of starting to, this is getting a little bit skewed, so maybe to make this more clear, I'll stretch it out horizontally for you, like that. Just keep zooming out. Well, by golly, what does this look like? It actually looks like a parabola. Right? It's a parabola. Now, have you ever heard of a parabolic asymptote?
Yes.
No. Doesn't really exist because the word asymptote implies a line. But conceptually, isn't there a parabola that this thing is forever and ever getting closer and closer and closer to? Yes. Could I find the actual equation of the parabola that is acting as the asymptote for this? By using long division. And we could graph that parabola and we would see it fit perfectly. Now the interesting thing is what infinity? The parabola? I don't know, what does that mean?
You take the denominator and divide it by, divide the numerator by the denominator, that's the asymptote?
Yep. So look at that. So there's some parabola coming through here, right? The general shape of this graph is a parabola, even though it has 1, 2, 3, 4 vertical asymptotes. Right?
Are those part of the graph?
Yeah. There's what part of the graph?
There's asymptote.
Well, the asymptote, the actual vertical line representing the asymptote is not a part of the graph. What's that?
If you expand it horizontally,
This is expanded horizontally. Huh. Uh-huh. Oh, yeah. My daughter loves it. You mean crawfish?
Yeah.
Yeah. seafood? My daughter loves seafood. She loves crawfish, oysters. Okay?
Have you tried oysters?
Oh, yeah. So, very, very parabolic looking, isn't it? The global scale, the general shape. 99.9999% of this graph just looks like some parabola that we could actually find the equation of. The small little portion in the middle, which is typically what we're most obsessed with, doesn't look like a parabola at all, right? Not at all. So that's the general idea of a rational function. If you take the degree of the top function minus the degree of the bottom, that degree will be the general shape of what this thing looks like. And so you just got to figure out where are all the asymptotes and intercepts in the middle. Okay, and you could use long division to actually get the equation of that polynomial asymptote. Okay? Yeah, let's do this. Why not? Here's a function, f of x equals 1 over x. What is its domain? All real numbers except for 0. So one of the ways you can write that is you can just say x does not equal 0. Oh, while I'm talking. Okay, x does not equal 0. Or in interval notation, you could say negative infinity up to 0, unioned with 0 up to infinity. Okay? Or you could literally write a sentence, all real numbers except for 0. I don't care. Yeah, that's right. Okay. What's the range? Range is a lot harder for these. You know, imagine being asked to find by hand what the range of this guy is. Well, that's actually not too hard. What is the range of this function? All reals. Right? Do you see a y coordinate anywhere? This single branch right here hits all the y coordinates, all reals, right? It goes up to infinity, goes down to infinity, there's no gaps in between. Now, not all rational functions are that way. Like 1 over x, for example. Look at that fraction. Can you tell me any number that you could not make that output? 0. The only way a fraction can be 0 is if the top is 0 and the bottom is what? Not. Right? The only way you can make this equal 0 is if the top is 0 and the bottom isn't.
But even if it's 0 over 0,
Oh, 0 over 0. What is 0 over 0? 0 divided by 0 is undefined. 0 divided by 0, that brings up a great question.
Great question.
What would this graph look like based on everything we've been talking about today? It's a degree 2 divided by a degree 1, so it should look like a line. But do you expect it to have a vertical asymptote in it? You would. Where would that vertical asymptote be? 3. What number makes the bottom equal 0? 3 does. But if you look more closely, what does 3 do to the top? It makes it equal 0. So, give me a number really, really close to 3. 2.9. Let's store that in for x. Then let's ask the calculator, what is x squared minus 9 divided by x minus 3? And it says 5.9. Okay, that's great. I expect, because the bottom of this fraction is approaching 0, what usually happens to a fraction when the bottom approaches 0? The fraction gets huge, usually, right? So what happens if I plug 2.999 in for x, and then I say, hey, calculator, do that again? Well, it didn't really get much bigger. What happens when if I plug in 3, what's the calculator going to say? It's going to say error, because that's 0 divided by 0. Well, hey now. Now that is your calculator rounding. It did not actually get 6. It did not get 6. In fact, this fraction can never output 6. It can't. There's nothing you can plug in for x that will make this output 6. Nothing. 3 is not in this graph's domain, 6 is not in this function's range. But, does this graph have a vertical asymptote? No. So what happens when we graph this thing? What was this? X squared minus 9? Oops, what did I just do? X squared minus 9 over x minus 3. GeoGebra gives me this. I don't see any vertical asymptotes. Now here's the thing, GeoGebra is not perfect. GeoGebra sure makes it look like there's a point at 3, 6, doesn't it? The reality is it isn't. There's a hole in that graph. Okay? So this graph looks like a line. It looks like a line, but with a hole in it. So 0 over 0 is still undefined, but it's not necessarily going to be a vertical asymptote. Okay? Whenever you have a fraction whose top is approaching 0, but the bottom is also approaching 0, it depends on how fast those things are going to 0. If the top is going to 0 at a rate proportional to the bottom, then the actual fraction could equal 13. Negative 8. Well, if the bottom is approaching 0 and the top is approaching some other number like 2, that's a vertical asymptote for sure. If both top and bottom are approaching 0, we don't know. We have to investigate further. And we'll be doing that. We'll talk about it.
So if the top number is approaching the positive number.
Or negative even. Doesn't matter. Any number but 0.
And if the bottom is
Approaching 0, that's a vertical asymptote for sure.
and if the top is not approaching 0. Wait, what? I meant a positive number.
If the top is approaching, give me a number. If the top is approaching negative 3 and the bottom is approaching,
0.
that graph has vertical asymptote. I don't know where. It depends on what number is causing it to alpha 0. But there's a vertical asymptote at whatever is making this happen. Does that make sense?
Homework.
Go ahead and start this homework. It's not huge. You can read the book. You can use your memory of Algebra 2. And we'll finish these examples tomorrow.